I'm here to talk about interpretability, which I think is a cool subject. I'm Alice, or Woog online. So here's a bit about me. I don't know how early to go. I was born in 1997. And then, yada yada. I did an undergrad at Carleton from Ottawa. And then after that, I found out that I needed life skills. So I learned programming. Then after that, I've been doing Mechanistic since. I actually had a phase of being a Discord e-girl, running my own little empire over there. So I have experience as being a Discord moderator as well, which is really compelling. Right now, I'm working at a Luther. Actually, I guess I have like 3 jobs right now. I have a grant from something called the Long-Term Future Fund, and teaching some AI safety fundamentals course. Okay, so this is actually the third iteration of this talk. So I've just been recycling the slides because they were pretty good. So it's not that one. It's not that one either because I only have 10 minutes apparently. I'm going to be talking a little bit about what mechanistic interpretability even is. And I'm going to talk a little bit about what I'm working on it, which is interpreting the weights of a model, sort of like all you need to run the model. So that work was started originally around 6 months ago. And then I'll say a little bit about what I'm working on right now at a Luther. So interpretability, what is it? It's like a neuroscience or artificial minds. So people are running these really, really big models in the wild and sort of interacting with people. But if something goes wrong, we won't really know why. And ideally, we would want to be able to sort of prevent things from going wrong before they go wrong. But that's kind of hard if you can either structure the outputs to be, you can force the models to sort of like be transparent somehow, or you can just read its mind. So interpretability is about taking the latter approach of just trying to directly read and write to the mind's thoughts. So this came originally from, I don't know if anyone actually recognizes this kind of image. It was really popular 8 years ago. It's called Deep Dream from Google. Raise your hand if anyone actually recognizes this. It was pretty popular. You didn't have to know about this stuff to come across it. So that's the Starry Night. It's some hallucinogenic rendition of it. A guy named Chris Olah sort of was interning at Google at the time, and he saw this project, and he really wanted to dive into it. So he picked this up as his pet project, and eventually it sort of took off, and he went to OpenAI, and he started a team there that works on understanding models on a more rigorous level using techniques inspired from this. And since then, it's gained some popularity. So, OpenAI has interpretability teams: Anthropic, DeepMind, Luther, Meta. Meta's interpretability kind of sucks, honestly. Goodfire, Martian, but lots of big companies. It's a pretty recent field, basically 4 years old only. They all have to do with these things called features. So let's talk about 2020 vision. Basically, you'll have a model, and models have weights. And you could look at these weights if you want to try to understand them, but as is, they're not super profoundly interesting. Chris's key insight was that you could apply the same kinds of sort of insights from this sort of deep dream project to sort of hallucinate an image that would sort of like optimally respond to sort of any neurons inside. And once you do this, you actually find some interesting stuff. It says that a car detector is really looking for windows on top of wheels. And so these are all just sort of like hallucinated, but maximally activating these kinds of things. Now, when you go to text, it doesn't really work anymore because you can't really visualize them. Google tried, didn't really work. You can hallucinate things, but they look like garbage. So people tried sort of indirect approaches. One of them is called causal interventions. You certainly get a graph, but the graph is unlabeled, so it's not very helpful. Recently, and nowadays, people take a technique called sparse coding, which does the sort of optimization process, but there's a problem. So this is from Anthropic. It's from sort of the academic lab, the guys at Anthropic now, but also OpenAI and Microsoft do kind of this work. The problem is that in this sort of new representation, the weights are gone. And so you sort of lose an important causal link in understanding the thought process. And so, so where do they go? So this is a long lost art in some sense, interpreting the weights. That's what me and some collaborators worked on. Maybe this talk is a little bit technical, but I'm trying not to go too much into the weeds here. It really rests on a math concept called bilinearity, and this is a really nice math property. And modern neural networks actually are almost bilinear. This is the structure of sort of like the hidden out layers in like Llama or Gemma or stuff like that. And if we just remove this little curly sigma there, we get something like this. And this makes the weights interpretable. Now this looks really, really contrived, but it's actually only 4 lines of code. And if you just pull these out, you can interpret them. So we did. So this is what happens when you try to interpret a vision model, one that try to classify handwritten digits. These are some digits, features for detecting a 4. So the top ones, if it aligns with the image, it'll promote predicting a 4, and if it aligns with the bottom ones, it'll demote. And so it looks like that 2s, 5s, and 3s roughly are kind of the opposites of 4s. And we didn't use any inputs to do this. It's only from the weights. It's completely intrinsic. But it's not limited to vision. We did it in languages as well. And it's not clear fully what's happening here, but this is kind of like our dumbed down version of that really big plot before. This is a logical AND gate. It sort of detects whether there's like positive sentiment in the text, as well as the presence of the word not. And if you have both of them, it'll flip it to a negative sentiment. And so like this is like a logical gate implemented in the weights. And so using weights is really important because it sort of grounds whatever reasoning process into the model itself and not only working on the heuristics level. So that was 6 months ago. Now I want to talk a little bit about a problematic statement that Anthropic made. They tried to do the same kinds of stuff that we did over here, these sort of small image classification models, but on something on the top form, and it didn't really work. And they concluded that small models are probably just pathological in some sense. So it's actually impossible to understand. Since we failed, it must be impossible. I think that's just a skill issue. So we worked on interpreting this. We don't have a direct analogy. And we saw that the features were not fucked up. They look kind of nice, actually. The open question is, can you do it over here? We think so, yes. Basically, yeah. So I kind of like speculated this on 3 months ago, and I worked on it for a couple weeks. And then I was like, it's probably doable, but I don't know enough math to do it. And then Nora reached out to me, and she said, well, tell you what, I'll do it for you. And if I do it, and you come up with nice experiments, I'll pay you to work on them. So that's cool, because I didn't even apply. They just reached out to me and offered me money, so I took it. And so now I'm working on them, and we're going to write a paper together. So actually, there is a way. Turns out that even though these guys are like kind of fucked up, and this thing gets in the way of understanding the weights, they actually end up implementing an almost identical function to this. And you can prove this mathematically. It's fairly sophisticated math. But once you do that, you can just get the closest fit of this to that and interpret that instead. Since they implement the same function, you can still understand the sort of intractable thing. So we'll be working on that and probably publish it pretty soon. That's all.
Does anyone have any questions?
Yeah. Yeah, go for it.
Thank you. Maybe I'm missing something, but like, what about attention layers?
Yeah, so we don't do attention.
Self-attention layers,
Yeah.
they can't be linear. They can't be bilinear as well.
Well, they're almost bilinear. The problem is the softmax and attention.
Right.
Yep.
So when you say almost, what do you mean? Like how do you measure this almost?
I measure it by the presence of an activation function here.
Right. But like how? So if you interpret like the second line here,
Yep.
do you have any estimate of how close this interpretation would be to reality?
So when interpreting this on its own, or when fitting it here?
When you interpret, like, as far as I understood, you're interpreting neural networks as if they don't have activations.
Okay, so in our earlier work, we trained them without activations,
Right.
and they still recover the same performance.
So you can interpret only those of them who, like, which have the same performance once trained without activations.
Yep.
Do you think it's a majority of neural networks with this behavior?
The majority of ones that are performant today.
So, like, you think we can take a transformer, like whatever architecture, remove activations, retrain it, and it will perform just as good as it performed with activations?
Yeah, I did it.
Okay. So,
It's actually in the paper that we did before.
and it is published already.
Yeah, well, this one is on archive right now, as of like a month ago. Yeah, cool. Appendix H. So it's on page 20 or something.
Any other questions?
So you explained a bit about the vision models, like about the language models, but how would these be like things like audio models or other type of models? Like would it be the same approach that we would already heard?
Yeah, so like I'm pretty optimistic about this approach, and generally, I mean, like the approach of kind of like not necessarily engineering interpretability into the model, but engineering the closest like nice mathematical version of it. Because once it's in a mathematical form, it's sort of automatically amenable to sort of all the math theory that exists in the world, which has been developed for 2,000 years. Right? We don't have to, engineer our sort of human understanding concepts of it, but just get it to the closest thing. And I think this is fairly reasonable for most, like it's not a large step away from kind of most architectures. Once you have a nice working architecture, you can just see which are like the big sort of like offending, method, like nonlinear things, and make it a nicer nonlinear thing. And I think if you smudge between like architectures, so we also did this in RL. So like reinforcement learning, we trained some reinforcement learning models on, and we just took every layer, the bilinear one, like all the layers that had non-nice activation functions, and we just changed them for bilinear ones, and it works. No, you don't even have to change the hyperparameters.
Hi there. I have a question. Do you know whether there are conditions under which the bilinearity doesn't perform very well compared to your first line?
Yeah.
Counter examples, for example.
So there's a nice paper. So I think this hasn't been explored enough, and I think it's something that I would like to see people explore. I think, like, obviously, it sounds like a free lunch kind of thing, right?
Yeah.
There's a I think there are settings. So we encountered this a little bit when doing reinforcement learning, that like I think when you do certain combinations of switches, it compounds a lot of like these kinds of things together that are like less stable to train over here, because when you like this is kind of zeroing out some activations, and this doesn't zero them out. And when you multiply them out together, it's possible for some sort of hidden activations to explode really, really quickly. In these models, you still get exploding things, but they're much, and you only really see it once you start quantizing models. Like there was a huge development of how like certain quantizations would like kill off a certain activation that the model was relying on. It was just, but you'll get a lot more of those kinds of things over here. So it's possible, for example, that if we have these kinds of settings that like, I don't know, I'm freely speculating right now, but it's possible that these would not be quantized well, for example.
Okay,
Yeah.
thanks.
Yeah.
One more question?
Sorry, this was like a really technical talk. I tried to make it, I tried to like also introduce the field and stuff like that. So.
Okay. Oh, one more question.
So, just a simple question.
Yeah.
Everything that you didn't mention yet, what was the hardest thing you had to solve to get to your theory to work?
Yeah. I would say probably the most recent stuff that I'm working on at Luther. The derivation for like making this fit over here was actually an open problem in math. So we had to like derive some new theorems, and it was like maybe like 5 to 6 pages of like integration and higher dimensional statistics that Nora actually did a lot of with OpenAI 01. But it was fairly new mathematics. I think for the previous one, we kind of got lucky. Lucky as in like, you know, the models that, the architectures that are performant today just happened to be really in this really like fairly close structure. We didn't have to do a lot, right? You know, one thing, for example, is like addressing attention. Like the interpretable architectures in some sense is like, you know, basically remove all bad math properties. One of them would be activation functions over here. Another one would be layer norms, and another one would be like the softmax in attention. And like to me, it would be ideal if we would remove all of them. There's some evidence that you can actually. There's been some recent work by Together AI where they removed the softmax in attention and turned Llama into a Mamba model, which is kind of interesting. But yeah, like I think you kind of, maybe I was just hoping I would get lucky in some sense. And we did get lucky. The hardest part was probably going from here, like the actual approximation fit here. Yeah.
Awesome.